Boolean algebra. In 1854, George Boole created a two-valued algebraic system which is now called as Boolean algebra. In 1938, Claude Shannon adapted Boolean algebra to analyze and describe the behavior of circuits built with relays. This adaptation is called switching algebra. So before going into Boolean algebra in depth, we have to first study about logic gates. Logic gates are the fundamental building blocks of digital systems. The name logic gate is derived from the ability of such a device to make decisions. That is, it produces one output level when some combinations of input levels are given and a different output level when other combinations of input levels are given. There are three basic types of gates, and those gates are called AND gate, OR gate, and NOT gate. The interconnection of these gates to perform a variety of logical operations is called logic design. Logic gates are included in electronic circuits and they are constructed in a wide variety of forms, usually embedded in large scale integrated circuits and very large scale integrated circuits along with a large number of other devices. Each gate is associated with a specific logic operation. Logic gates occurs in two levels, that is either high and low or true and false or on and off or numeric 1 and numeric zeros. Okay, and the in a table which lists all the possible combinations of input variables and the corresponding outputs is called a truth table. It shows how the logic circuit's output responds to various combinations of logical levels at the input. Okay, and logic level can be categorized as positive logic or negative logic. Positive logic system is one in which higher of the two voltage represent the logic 1 and the lower of the voltage levels represent logic 0. A negative logic system is the one in which lower of the voltage level represent logic 1 and higher of the voltage level represent logic 0. Now we can see each of the gate in detail. First is the AND gate. AND gate has two or more inputs but only one output. The output assumes the logic 1 state only when each of its input is at logic 1 state. The output assumes the logic 0 state even if one of its input is at logic 0 state. The AND gate therefore may be defined as a device whose output is 1 if and only if all its inputs are 1. Hence, the AND gate is also called as all or nothing gate. The logic symbol and the truth table of a two-input AND gate is shown in the figure. Note that the output is 1 only when all the inputs are 1. And the symbol for AND operation is a dot. That is A, B or A dot B both represent A and B. Next is the OR gate. Like an AND gate, an OR gate may have two or more inputs but only one output. The output assumes the logic 1 state even if one of its input is in logic 1 states. Its output assumes the logic 0 state only when each of its input is in logic 0 state. An OR gate therefore may be defined as a device whose output is 1 even if one of its input is 1. Hence, an OR gate is called an any or OR gate. The logic symbol and the truth table of a two-input OR gate is shown in the figure. And note that the output is 1 even if one of its input is 1. The symbol for OR operation is plus. So, x equal to or c equal to a plus b, that is a or b. If the value of a is 0 and b is 0, what is the output? Output will be 0. If the value of a is 1 and b is 0, what is the output? The value of c, which is the output, is 1. So the next type of basic logic gate is the NOT gate. NOT gate is also called as an inverter, and it has only one input and only one output. It is a device whose output is always the complement of its input. That is, the output of a NOT gate assumes the logic 1 state when its input is in logic 0 state, and assumes the logic 0 state when its input is in logic 1 state. The logic symbol and the truth table of an inverter is shown in the figure. The symbol for NOT operation is a bar. So when the input variable to the NOT gate is represented by A, the output variable by X, the expression for output X is equal to A bar. So in the figure, output variable C and the input variable is A. Therefore, the output C is represented by C is equal to A bar. Though logic circuits of any complexity can be realized by using only the three basic gates, which are AND, OR and NOT, there are two universal gates also, and those are called NAND and NOR, each of which also can realize logic circuits single-handedly. So the NAND and NOR gates are therefore called as universal building blocks. Both NAND and NOR gates can perform all the three basic logic functions, that is AND operation, OR operation and NOT operation. So the next type of gates you need to familiarize is called the exclusive OR. It's also represented as XOR or EOR. An XOR gate is a two input, one output logic gate or logic circuit whose output assumes a logic 1 state when only one and only one of its inputs assumes a logic 1 state. Under the conditions when both the inputs assumes the logic 0 state or when both the inputs assumes logic 1 state, the output assumes a logic 0. Since an XOR gate produces an output 1 only when the inputs are not equal, it is called an anti-coincidence gate or inequality detector. The output of an XOR gate is represented as the modular sum of its two inputs. The name exclusive OR is derived from the fact that its output is a 1 only when exclusively one of its input is a 1. The logic symbol and the truth table of a two-input XOR gate is shown in the figure. And here the output is represented as A XOR B. A and B are the inputs given into the XOR gate, and the output is represented by using a plus, which is encapsulated by a circle. So that is the symbol used for exclusive OR gate. The figure represents various types of gates. The first is the AND gate that you have already familiarized, where A and B are the input and the output is A dot B, or simply written as AB. And on the right side we have AB, which is OR, and the result is A plus B. And the third one is we have given a NAND gate. So NAND gate is a combination of AND gate and a NOT gate. That is A and B when is given to a NAND gate, and then we can see a bubble at the end of the AND gate. So AND gate followed by a bubble is called a NAND gate, and the output is AB the whole bar. Similarly, we have a NOR gate. So NOR gate is a combination of OR gate and NOT gate. So if we have put a symbol of OR gate followed by a bubble at the end, then it is called as a NOR gate. And the output is represented by A plus B. So that is the output of OR gate, and then invert it. So invert it will result in A plus B the whole bar. Then we have seen a NOT gate. So A, when given to a NOT gate, the output will be A bar. And then we have XOR gate or EOR gate, where A and B, when you give us input into the XOR gate, you get A XOR B as the result. We can also have XNOR gate, where when we put a bubble at the end of the XOR gate symbol, it becomes XNOR. Show that A XOR B is equal to A B bar plus A bar B. construct the corresponding logic diagram. So if this is the case, first you have to find out the LHS and then you have to find out the RHS and state that LHS is equal to RHS. For that, for finding LHS, the value of LHS, we have the inputs A and B and write all the possible combinations of the inputs, which is 0, 0, 0, 1, 1, 0 and 1, 1. And A XOR B, if we perform, you get the values as 0, 1, 1, 0 correspondingly for the given inputs A and B. And for RHS, you have the inputs A and B, write all the possible values of A and B, and then you have to create a column for A bar, which is the complement of A, and you get the values as 1, 1, 0, 0. Then you have to create a column for B bar, which is the complement of B, that is 1, 0, 1, 0. Then you have to find out A bar B. Perform AND operation on the column A bar and B. You get the values as 0, 1, 0, 0. Then create a column for A B bar. A B bar, for creating, what you have to do? You have to perform AND operation between the column A and the column B bar. You get the resultant values as 0, 0, 1, 0, 0. Now you get A bar B and A B bar. Perform OR operation on these two columns to get the result as 0, 1, 1, 0. So the result of the RHS and LHS, you get the value as same. So thus we have proved that LHS is equal to RHS by constructing the truth table. So next is to construct the corresponding logic diagram. So LHS is performing an OR XOR operation only. So I can directly use an XOR gate where inputs are A and B and obtain the output. And for constructing the RHS, we have the inputs A and B. You can invert A by putting a NOT operator and then give the input B and A bar into a AND gate. Similarly, perform NOT operation on B, which is B bar, and then give input to an AND gate from A and B bar. So two AND gates are used here. The first AND gate will obtain a result as A bar B, and second AND gate will obtain the result as A B bar. And then you give these output of AND gates to an OR gate to obtain the out. Once you have familiarized with logic gates, you can move into Boolean algebra. Boolean algebra is an algebraic system which consisting of set of elements as 0, 1. It contains two binary operators which are OR and AND, and one unary operator which is a NOT operator or NOT logic gate. Axioms and postulates are available in Boolean algebra, which are a set of logical expressions upon which useful theorems can be built. The various axioms available are: when 0 is AND with 0, you get the value as 0. When 0 is AND with 1, you get the value as 0. When 1 is AND with 0, you get the value as 1. And when 1 is AND with 1, you get the value as 1. And for OR operation, we have 0 and 0. When you perform OR operation, you get the result as 0. And similarly, 0 or 1, you get the result as 1. 1 or 0, you get the result as 1. 1 or 1, you get the result as 1. Then we have NOT operation axioms, that is 1's complement is 0 and 0's complement is 1.